The purpose of this tool is to address the question, what is the best combination of electrification options and energy carriers to decarbonize passenger cars? To address this question, we have developed this interactive tool, which provides guided scenarios, allowing you to compare life cycle emissions from passenger cars, function of your own use case that you will be able to design, and your own sensitivities according to several set of parameters. We have a first set of parameters related to the configuration and the design of the vehicles. Your vehicle can be a hybrid car, a plug-in hybrid, or an electric car. You can also select the size of the battery and the emissions related to its manufacture, and you can also select the lifetime of your car in terms of mileage. The second set of parameters is related to the usage of your vehicle. You can define in our tool your typical trip profile, especially in terms of distance, the climate conditions in which you drive, and if you have a plug-in hybrid vehicle, the recharge frequency. Last but not least, the last set of parameters is related to the energy carriers, and you will be able to set the carbon intensity of the electricity used and the fuels with fossil-based options and renewable-based options. So how does it work? In our tool, everything is based on experiments. We have tested 2 plug-in hybrid electric vehicles. You can see one of them on the right-hand side. And we have tested them extensively. I mean, they have been tested in laboratory conditions and on the road to make sure that it is aligned with real-world data in a wide range of temperature between -2 and +35 degrees. They have been tested with several fuels, gasoline, diesel, and renewable fuels. And we have also varied the recharge of the battery for the plug-in hybrid vehicle. We have tested it either recharge or not recharge, and with various driving profile from the smooth urban driving conditions to the dynamic highway driving conditions. And all the data we have collated have been used as inputs to the creation and the calibration of a simulation platform. So this is what the simulation platform looks like. I'm sorry, it's a little bit complicated, but just to show you what it looks like, this has been designed by IFP Energy Nouvelle, which has done an amazing work in calibrating the tool, and it has been calibrated to fit the data that we have collated. But we haven't stopped here. From the plug-in hybrid electric vehicle simulator, we have also created 2 other simulators. Another one for a non-plug-in hybrid vehicle. It's very simple to create it. You take a smaller battery, it's a lighter vehicle, and you don't recharge it from the grid because it doesn't have a plug. And we have also created a simulator for a battery electric vehicle, an electric car, and it was quite easy to create it because you take a bigger battery, you remove the internal combustion engine, and you drive in full electric mode. Of course, in reality, it is more complex than this, but in simplified words, this is what it looks like. The next step was to design use cases, and you can see an example of that here. You can see, according to the trip distance you drive every day, the probability density you have to drive this distance. Because defining a use case is not just defining one trip. It's just not one trip of 20 kilometers. It's just not one trip of 80 kilometers. It's a family of trips. And it has to be defined by the probability you have to drive these trips. And so we have extracted that from the scientific literature. And you can see that the very short trips, 1 or 2 kilometers long, are not very likely. The rather short trips, 5 to 10 kilometers long, are very likely, and the very long trips, 400, 1,000 kilometers long, are not very likely, but of course they have a heavy weight because they are very long. And so thanks to the simulator, we were able to simulate each of these trips one by one, so the 1 kilometer long, the 2 kilometer long, the 5 kilometer long, and the 1,000 kilometer long. And we have weighted the results of the simulations according to 2 parameters. the probability density that is displayed here, and the distance of the trip. So the longer the trip, the heavier it weighs because it consumes more energy. We have put that together in a statistical model. It took us more than 50,000 simulations and 2 years of work to do that. So it's a huge amount of work that we have behind. And at the end of the day, thanks to that, we are able to evaluate what is the real-world performance of different use cases and different vehicles. So I'll just share with you an example of what it looks like and how you can read the results. Here it's an example showing the utility factor of a plug-in hybrid electric vehicle. The utility factor is the share, expressed in percent, of mileage that you drive in full electric mode, knowing that the remaining part is driven in thermal mode. Here you can see for different vehicles, depending on the size of the battery, between 2 kWh, which would be very small, and up to 35 kWh, which would be very big. And also depending on the recharge frequency, up to recharging it twice a day. This is the dark blue curve. Then you have a recharge every day. This is the orange curve. Then you have a recharge only every 2 days. This is the yellow curve, every 3 days, and so on until every 10 days. And once it's generated, thanks to the simulations, you can read the results out of the curves. So for instance, if you have a plug-in hybrid vehicle with a 15 kWh battery and you recharge it every day, you can read the utility factor, which would be 77% in this use case. If you have a smaller battery, 10 kWh, and you recharge only every 2 days, then the utility factor would drop down to 48%. And another use case with an even smaller battery, 5 kWh, and you recharge it only every 5 days. In this case, the utility factor would be 28%. So this is just one example on one parameter with one use case of what we have generated. And of course, we have also generated that for other parameters, such as the CO2 emissions at the tailpipe, the fuel consumption, the electricity consumption, and we have generated that for several use cases. So this is what is behind our tool. This is the core of our tool. Here you can understand what is in our tool seen from the tank to wheel perspective, and our tool connects this with the well to tank perspective and the life cycle perspective with different scenarios.